So let's move on with our understanding of oscillations. What happens now is that we have already understood that if a body is in simple harmonic motion, the force is directly proportional to displacement, and it's a restoring force, so we put a negative sign. And we further said that F is equal to minus kx, and we further said that ma is equal to minus kx, and then I am saying that m d squared x by dt squared is equal to minus kx, and this we have solved it. Okay, now before we move ahead, let us look at some cases where such a situation arises, so that will give us a basic understanding of what is simple harmonic motion. Now suppose I have a spring. A spring has a spring constant of k, and it has a mass m attached to it. So if I have a spring and then I stretch the spring by some distance x naught, then what happens is that there is when I make it in this direction, when displacement is in this direction, the spring pulls it in this direction, so that is, it is pulling the mass towards its mean position. So I can call this a restoring force. So I can say that F is equal to minus kx. So now this is a situation of this kind. So I can say that this body, the motion of the body is simple harmonic. Now one thing we have to be very clear. See, here we are saying that the force is equal to minus kx. That means if x increases, force increases. Usually it happens within an elastic limit. So if you extend the spring too much, the extension will not be proportional to F. Hence, in most cases of simple harmonic motions, they say for simple oscillations, or they say for small oscillations. That is, if the amplitude is small, I can say that the motion of a body which is connected to a spring is simple harmonic. Okay, then once you understand this, then things become much easier. What's happening is, look, when I stretched it here, the external force is doing work. When the external force is doing work, the spring gets stretched. Then when the spring gets stretched, the potential energy of the spring increases, and when the potential energy of the spring increases, there is more energy stored. When you release it, the spring pulls the body. When it pulls the body, the spring is doing work. When the spring does work, the kinetic energy of the body increases. The stretch in the spring decreases, so potential energy decreases, right? So what happens in oscillations is, there is a constant transfer or interchange between potential energy and kinetic energy. When you initiate a simple harmonic motion, the potential energy increases, and subsequently what happens is there is a conversion between potential energy and kinetic energy, and vice versa. So now as the body comes back, it gains in kinetic energy and it has reached its mean position. Once it is there in its mean position, it has only kinetic energy. But now because of inertia, it continues to move in this direction. Now as it moves in this direction, the spring gets compressed and it pushes it in this direction. So the kinetic energy now again gets converted into potential energy. So there is, in a constant way, there is an interconversion between kinetic energy and potential energy. Okay, now if I have to draw a graph, so let me first draw the diagram once again. When the spring is stretched, all the energy is in the potential energy form. When the spring is in its mean position, all the energy is in the kinetic energy form. When the spring is compressed, all the energy is in the potential energy form. Again, once it's fully compressed, it stops. The compressed spring pushes the mass. So again the spring gets stretched. It goes to its mean unstretched position. All the energy is in the kinetic energy form. Again, because of inertia, it continues to move, and then again it gets stretched, and all the energy is in the potential energy form. So what happens is, there is a constant change, or there is a constant conversion of kinetic energy to potential energy. Initially the potential energy is high, it becomes 0, and then it becomes kinetic energy. Then the potential energy again increases. Initially the kinetic energy is 0, it goes to its maximum value, and then again it comes down. That means when the potential energy is equal to 0, the kinetic energy is max. When potential energy is equal to max, the kinetic energy is 0. Okay, such that because there is no loss of energy anywhere, the total energy is a constant. So total energy is a constant means potential energy plus kinetic energy is a constant. So in this kind of a system, the total energy is constant, that is potential energy plus kinetic energy is constant. I can say potential energy is half kx squared. I can say kinetic energy is half mv squared, and this is equal to a constant. That's the total energy. Now suppose I differentiate this, I'll get half k 2x into dx by dt plus half m 2v into dv by dt is equal to 0, because differential of a constant is 0. Now dx by dt is nothing but its velocity, then this 2 gets cancelled, so kx into v plus this 2 gets cancelled, mv into a is equal to 0. I can take v common, I can have kx plus ma is equal to 0. Now v is not equal to 0, so this must be 0, so kx plus ma is equal to 0, right? So this is what we at the beginning we defined, that if a body is in simple harmonic motion, this is the equation of its motion, or this equation represents its motion. Okay, so now we are learning two things. One, not only that this equation represents the motion if a body is in simple harmonic motion, two, its energy is a constant, that is potential energy plus kinetic energy is a constant. Okay, so this is the other understanding that we are having. To give you an example of simple harmonic motion, the motion of a mass connected to a spring is an example of simple harmonic motion. Okay, so we will look at different examples so that we are able to understand this a little better. Okay.